We now formalize our idea for solving nonlinear equations or finding approximate solutions to nonlinear equations in a method called Newton's method. The first step is we start with an equation. So the idea is we have an equation in front of us that we cannot solve by hand, but we can convert it into a simple form, f of x equals 0. And we can always do that. We just move whatever is on the right to the left and change its sign. Our next step is to choose a starting value, let's call it x naught, near a root of f of x. And remember, a root of f of x is going to be a solution to the original equation. Then we're going to do something that might look a little exotic. We're going to get a new x value from our old x value based on this formula here, which has a function and an f prime in it. And what that's going to do for us is find the root not of the formula of the function, but of the tangent line to that point. And so we're going to take one x guess at the solution. We're going to get a new guess that we think is better, and then we're going to go back and do that formula again. And we're going to keep updating our oldest guess to get a new guess until we get something that's close enough for our purposes to the root. So it's iterative, and we choose when to stop based on our accuracy goals. For the purposes of this class, we're going to do this 2 to 3 times. All right. That mysterious formula in step 3 turns out it has a very solid mathematical basis for it. So let's imagine a function, f of x. So f of x is here. We pick a point on the function. There we go. And we're interested in knowing when that tangent line is going to cross the x-axis. Okay. Well, for that, we have to know what the linear function is. So the idea is the linear function is a function of x, and it is f prime at the point we are considering times x minus the point we're considering plus f of xn. And here, xn is like our earlier a value, our fixed point on the graph. So this would be xn, the fixed point on the graph where we're drawing the tangent line. The x is the variable. And what we want to do is solve for the y equals 0 or x-intercept, which means that we need L of x to equal 0, which means that f prime of xn, x minus xn, plus f of xn is equal to 0. The value we want, this little coordinate here, that's the x value we want where the tangent line hits the x-axis. What x coordinate is that going to be at? We want to solve for that. And so we just move everything over piece by piece. Bring that to the other side. Then we're going to divide through by f prime of xn. And last but not least, we bring this to the other side. It becomes positive. And so this is our new x root approximation. Is going to be our old one minus the function value divided by the derivative. That's not obvious, but it comes directly from solving for the location where the tangent line is going to have its root or x-intercept. Okay, let's take a look at the example we had before. So this was our function, and we had f prime of x calculated already, minus 10 e to the minus x plus 1. And our x naught, our guess at the root, our first guess at the solution, was 0.5. Okay. So what I usually do is try to build a table. And so we say we start at 0.5. What values do we need? Well, we're going to need, keeping in mind our function or our xn plus 1, our new x is our old x minus our function at x minus the derivative at that same old point. We're going to need the function at xn, and we're going to need the derivative at xn, and then we're going to probably put all that together. There's different variations on this about what you actually put in the table, but these two ingredients are essential. All right, let's take the 0.5. We plug it into our formula here. We're going to get a value that's roughly negative 0.43. We plug this same x value into the derivative. We're going to get approximately negative 0.506. We saw that earlier. Now, if we try to combine these things, so we take 0.5 minus this over this, we're going to get a value of approximately 0.414. And the important thing to remember is this is our x new or x n plus 1. So this literally gets copied down to here. It's our next best guess for the slope, or sorry, for the location of the root. Okay, so this is our, we think 0.5 is close to the solution here. I think 0.414 is closer still. And now we're going to go through this one more time. I'm going to plug the 0.414 into our function, plug the 0.414 into our derivative, and then plug all three of these numbers into this formula here. And when we do that, we get a number like 0.4183. That becomes, again, our new guess. And what you notice, actually, is that these two numbers are the same for the first two decimal places. That's a sign that we have converged, or we're close to converging. And so this is probably a very good estimate of the value of the function here. In fact, we can test that by taking this number and plugging it in. And if you do that, you get a number that's 6.05 times 10 to the negative 5. And for most stuff in a math class, that's very, very close to 0. So what's the translation? If we plug 0.4183 into f of x, it becomes approximately 0. Well, that means x equals 0.4183 is a solution to 10 e to the negative x plus x minus 7 equals 0, is an approximate solution. Again, it's very close, but it's not going to be entirely perfect because we could have more digits on the end here. But we plug 0.4183 into x and x here, we'll get something that satisfies this equation. Estimate the quality. Well, if x is equal to 0.4183, let's check it by plugging it into that equation. 10 e to the minus 0.4183 plus 0.4183. Our original equation had a 7 on the other side. So let's remember the original equation, 10 e to the minus x plus x equals 7. We do this calculation. We're going to get 6.9995. That's our left-hand side. And our right-hand side is just 7. And yes, indeed, these two numbers here are incredibly close. And so we can confidently say that this value is as close as we probably care for this contextless application to the right x value, to the exact x value. It's very, very close. because both sides of the equation are very, very close when we sub it in. And so that's some reassurance. 0.4183 is a very good estimate. And just notice that caveat. It's an estimate, not exact, of the solution, or of a solution to the original equation. If we want to sketch the values we computed, the values we had were 0.5, negative 0.43, and then we went into about 0.41, and we ended up with a positive values around 0.2 something, and about 0.4. And what you can imagine is the curve goes through this. We've calculated some very detailed points in this, and what we get as a sketch of the curve in between is a root right here around that 0.4183 value that we saw. So we get a very good zoom in on the actual coordinate of the root. Again, not exact, but a good approximation, pardon me. And it's all based on tangent lines. Whoops. Let's clean that up a little bit. All right. When we drew tangent lines at each of these various points, we got very close to the root that we were interested in. We can do more detailed sketches with some computers, but I think the main illustration here that's required is just knowing that we follow the tangent lines to a point, we follow the tangent line to a point, we keep doing that, and because we're zooming in and the tangent line is getting closer to the original function, we get more and more accurate results with each iteration. Little caveat on that, there are certain conditions on whether this is going to work in every case, and it also requires a sufficiently close initial estimate of the root. We can't just start anywhere. So many students find this uncomfortable, trying to find an initial root. Just try some values, see which one gives an approximate solution to the equation. Do both sides equal each other? Are they close to equal? That gives you a good estimate of the root. And just keep in mind, the output of Newton's method is always just an estimate. It's a numeric value that's going to be close to, but not exactly equal to, the solution to the equation.